The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so this lecture is primarily of historical interest, although it addresses a very fundamental problem, and that is when you have a data set that contains an enormous amount of information, there should be some pattern recognition schemes that you can use to harvest the information. And so I'm going to illustrate some pattern recognition schemes that were used by the old-time spectroscopists. What they would do is they would have a big spectrograph, and they'd have a photographic plate, which was about 2 feet long and maybe 3 or 4 inches high, glass, so that it's mechanically stable, and they would have a spectrograph with slits that are 10 microns wide. And so you have here 600 millimeters. How many resolution elements are there in that 600 millimeters? It's on the order of 100,000. And what they would do is, because film has a very poor dynamic range, maybe a factor of 5 or something like that, from something that's too weak to something that's starting to be too broad, they would record a this spectrum, and they would have a little thing in front of the slit. It would be sort of like this. And so they would have the whole slit open, and then they'd push this in front of the slit and block the bottom part, and then the bottom half and the bottom 3/4. And so they would have different exposures. And so it would be possible to capture weak lines and strong lines, and to be able to measure their frequency accurately using what was called a comparator or a traveling microscope or whatever. And initially, in the old days, people would turn a crank on this thing that could measure the position of a line to better than a micron. And they would be looking through a microscope, and they'd watch the lines translate onto the crosshair. And then they would either push a button and something would get written down automatically, or they would write it down, because in the old days there was no electronic. So anyway, the information on this consists of on the order of 10 to the 5 resolution elements, with some information about intensity. And it would not be unusual to have on this plate 1,000 or even several thousand resolvable lines. And so what do? You get this enormous data set, and whether you did it completely by hand or with some computer assistance, you have thousands of lines measured to on the order of a part in a million in their frequency. And how do you begin to make sense of what's here? The first thing that you don't do is look at band contours, because and say, okay, we're going to have a computer and we're going to look at this and we're going to see structures and we're going to try to fit the overall pattern to a model without individually assigning the lines, because the patterns are more complicated, and any sort of automated procedure would almost always get it wrong, and it would certainly miss the crucial details. So the whole reason we have to do this is because bands have heads, and so one branch goes along to in one direction, turns around, comes back, and you can't count the individual lines. And it also obscures the beginning of the other branch, and so you have to use some clever tricks to dig out the crucial lines. It's actually worse than that, because if you took the R and P branch lines and converted these formulas for the R and P branch lines to a single formula, you get an equation called for a four-trat parabola. And so all of the lines in the R and the P branch can be fitted to one parabola, and there is no way of absolutely numbering the lines in the parabola. If you change the numbers, you get the same parabola, and so you can't, by somehow recognizing a series of lines and fitting it to a quadratic form, that you could get an assignment. You just can find a whole bunch of lines that are related to each other, but you cannot know their rotational assignment. And this is a bad piece of news. Now, I was going to derive the equation for the four-trat parabola, and should I do that? Do you want me to do it? I mean, it's pretty horrible, tedious.
It's not that complicated.
It's not that complicated. But the important thing is these two equations can be combined into one, and then once you have that one equation, if you change the numbering of the lines by just adding a constant, you get, adding an integer to the running number, you get the same equation. You get this, and so there's nothing unique about that equation. So how do we find the absolute rotational numbering? Now there's methods for doing this that start with knowing nothing. And there are methods for doing this where you start by knowing the rotational constant for some vibrational level, usually the ground state. So it's very common in spectroscopy that you have a whole bunch of bands observed from a common level. And so once you know the rotational constant for this level, then you're in a position to be able to make an analysis of any of the other bands based on knowing the lower state combination differences. Now, we have lasers, and we have techniques now where we don't have to depend on a brute force pattern recognition. But I think it's really useful to explore the methods that had been used, because whenever you have a spectroscopic technique that is capable of generating 100,000 resolution elements in a single shot, which is what we have, that there has to be some clever way of harvesting the information in that. Because if you didn't, one spectrum could occupy you for a lifetime, and mostly is nothing interesting, or not much interesting, but you don't know until you've laid waste to this whole thing. So you'd really like to be able to know what kinds of pattern recognition techniques had been used, and when do they work, and how robust are they? So if you have all right, so let's just draw this. Now, these are two rotational levels of the ground state, or the known state. And so you might have J minus 1, J plus 1, J. And so that would be the R branch. So this would be R J minus 1, and this would be P J plus 1. And those two transitions are to a common upper state. And they're different, their frequency difference is a known rotational energy interval. That rotational interval you can calculate is the rotational constant for the ground state times 4J plus 2. And so if you know the rotational constant downstairs, you will be able to see rotational combination differences changing in steps of 4b. So provided that the lower state is unperturbed, is simple, then you can simply describe all of the possible rotational intervals by this formula. And this leads you to something that I truly love. It's called the Lagerfeld strip. And almost all classical spectroscopists used a method like this. They would take from their spectrum all the measured lines and plot them on a piece of paper. They might put information about the intensity, but they would simply plot them on a scale linear in frequency. And they would usually do this in ink on a piece of paper, strips of graph paper scotch taped together, and they would always make joins like this, because those sorts of joins are more rugged than if you have a vertical join. You know, the technology is fantastic. And of course, when you do that, then you match the crossbars carefully. And so you might have a strip of graph paper, many tens of meters long, with drawn on it all of the lines that are observed. And it is very common to use a scale 1 centimeter per reciprocal centimeter. Just, you know, that's what you do. Because the precision of measurement is on the order of 1/100th of a reciprocal centimeter. And so that's just about enough space to be able to represent each line to the accuracy with which it was measured. Okay, and then you would make another strip, not as long. And you would have a 0 here, and you'd have 2b, 6b, 10b. Except it wouldn't just be B. It would have the centrifugal distortion that you know as well, because this is supposed to be really accurate. I mean, you know the lower state intervals, and the only way you can avoid screwing up is to take perfect advantage of the precision of the measurements and the precision with which you know the lower state combination differences. And so what you would do is you would look at the spectrum and you would see, oh, by eye, I see 3 or 4 or 5 lines that look like they're regularly spaced. Regularly spaced in frequency and with similar intensities. And so you say, aha, I think I have the beginning of something. And so you take one of those lines and you put this 0 above or below it, and then you look into the dense forest of unassigned lines for coincidences with rungs on this strip. And so you might find a whole bunch of coincidences. Does everyone understand? I mean, I think it's so beautiful. It's so simple, you know, but you know, it works. It doesn't matter how complicated the spectrum is. You can always make sense out of it, provided you know you have enough precision. Okay, so you find a little patch of regular behavior which you think is real, and you put the 0 on it, and you look for. So say that's an R branch where you're looking to the blue, to the red for the P branch that goes with it, or if it's a P branch, you're looking to the blue for the R branch that goes with it. And so you're going to be willing to turn this ruler upside down. And then you make a little list of all of the possible coincidences with this line. What are they? And then you move the ruler, the 0 of the ruler, to the next line in the pattern. And you're going to find some coincidences. But most of the coincidences you found on the first observation will turn out to be spurious, because there won't be anything that corresponds to the next rung, the next higher j on this ruler, or the next lower j on this ruler, for several of those coincidences. And so very quickly after, if you have a legitimate few line pattern, you are beginning to say, oh, well, this obviously was P17, and the next, you know, I've linked it up with R15, and now I found P18, and it's linked up with R16, and you're off to the races. And sometimes you find bona fide coincidences for more than one, you know, so you have a P line and you have an R line, but you find 2 R lines that work. And you can, and that's okay, because you can, I'm saying it wrong. You will find 2 pairs of lines with the right lower state combination difference, and they will correspond to, say, an extra line. In fact, that's what they called it. If in the spectrum, and now we're plotting energy versus JJ plus 1, if there's a level crossing, there can be a perturbation. There can be, so this is supposedly the line, the band we're interested in. And this is the band that we weren't supposed to see, but when they cross, there's some intensity borrowing and level shifts. And so it's quite possible to have 2 lines of the same J that appear only over a very small range of rotational levels. And so you just use this Lagercrest strip, and you make these tables, and so you have a bunch of lines, and sometimes you have an extra line at that J, and so you put them into a different column. And actually what frequently happens is that you get a column shift, because the regular series of lines, sort of when at the perturbation, you're following a series of lines, and when something like this happens, you get a few extra lines in this. You want to go back to that track, and so they would tabulate these. You'd have a table of lines, and it would end, and there would be a little overlap, and that's the way it was done. Okay, so now I want to show some pictures. You have this in your notes, but there'll be some that I'll be showing that you don't have in your notes. Okay, so this is a picture of a very simple electronic transition that looks easy to assign. You see this zero gap here. You see the regular series of lines. You see this bandhead. There is a bandhead here. That makes life complicated. But it's not very complicated because it's far enough away from the band origin, where there's this nice gap, that the lines don't have much intensity when they start coming back this way. And so it looks just, like a textbook. In fact, it's better than a textbook because nothing should look that good except this particular band. And then if you look at the next vibrational band in the same electronic transition, it looks like that. And so what is this? Well, these are, the upper state is perturbed multiply, and so we have several groups of lines that get assigned using this logarithmic strip, because the strip doesn't care about the perturbations upstairs. It's using the regular intervals downstairs. And so the final product of such an analysis is this labeled diagram where you have the branches, the rotational transition, the rotational number of the R and the P branch, and these shifts that indicate perturbations. So once you have that, then you can take the energy levels from this diagram and fit them to a model. And in the old days, the models that were used were entirely graphical. And there were ways in which you would plot the data to, instead of fitting it to, by straight line plots, get the B values and the origins of these bands. And it worked for years, and there's a highly algebraic approach because there were no computers. And if you had too many interacting components, you couldn't use the quadratic formula, and so you just had to use clever graphical methods. Now, there are some states where you automatically get many interacting components, like anything other than singlet sigma. And so it is very common to have something that is very much suited for a computer, but for the old-time spectroscopists, before computers came, it was mostly finished. There wasn't anything that you couldn't really do by the classical techniques, except it was very slow. And okay, so let me turn this off for a second. So I have a problem I've used on exams before, where I give you a series of lines for a fictitious molecule which I call drechium oxide, and drechium is in the same column of the periodic table as barium, and so it's below barium somewhere, and it has a perturbation in it, and you can use the logarithmic strip or some computer manifestation of the logarithm. This is a perfectly easy thing to implement using a computer. You don't have to make these strips of paper anymore.
Using the strips of paper, though, gives you a sort of approximate, you get to look and sort of judge, is this line close enough to, right?
Yes, you do.
You can do that on a computer pretty easily, too.
You can do that, too. But, I mean, the wonderful thing about the spectrum is that there's a lot of information that that you see. The intensity and the shape of the line. There's just things you can tell by looking that, yes, you can do that using the computer, but your pattern recognition sense is still pretty sophisticated compared to what a computer can do. And so you do want to be able to look at the file and say, are the intensities right? Is there an error here? Do I accept this? And there's a lot of sophisticated decisions. And certainly you can build artificial intelligence that will do that. But it's not trivial. And I think learning from what the old-time spectroscopists did, especially if you can get a sense for what are the methods that were used by the people who never made errors and always were able to deal with complicated spectra? What did they use? And Lagerfeld is notorious for having only one paper that had anything wrong in it. And he always went for the most complicated bands, except for his friend Richard Barrow, who liked to do even more complicated things, but they used the same method. And Hertzberg used to tease them about their strips. But Anthony Mehrer Anthony Mehrer was a student of Richard Barrow, and so if Barrow did it, Anthony did it. Okay, so you can use these things, but not in your notes is something that I really want you to see. This is called a Loomis wood plot. And what is this? What is this here? So this is something that you would do when you know nothing. You don't know what the molecule is, you don't know what the transition is, and there's so many lines that you have trouble picking out more than fragments of patterns. So Loomis and Wood were, I forget when they published most of their stuff. It was in the early part of the 20th century, before 1930 certainly.
Wood was most active in the 1910s and 20s.
That's right.
Especially 20s.
And so they developed a method, and what the method is you look for what looks like a regular series of lines. And since a regular series of lines is almost always fittable with a quadratic equation, because we have 4-trat parabolas, you just say, oh, these things, I recognize these lines, and I'm going to fit it to a quadratic. I don't care what the numbering is, because that's something I need to figure out. But the way I figure that out is by extending the pattern. And if the pattern is going into a bandhead and coming back from the bandhead, it's not a trivial matter to extend the pattern without some graphical tools. So what you do is you say, okay, I'm going to pick this member of the pattern. And then I'm going to calculate the differences. So I'm going to convert the one-dimensional pattern with intensities into a two-dimensional pattern. This seems like you're going backwards. But what you really would like to do is to recognize the members of this pattern that belong together, without making any assumption other than saying, I'm starting here, I see something. And so what you do is you pick this, or you say, well, this is number 23. And I calculate the differences between all of the lines not in this pattern, this line and all the other lines within an interval you've decided is going to be big enough to capture other members of the pattern. And so this line then generates a whole bunch of spots. And these spots, these points, are color-coded according to their intensity. On here, they're not color-coded because this is black and white. But you can see some of them are darker than others. And so you do this now for all of the lines in this pattern. And so you've labeled these lines by an integer. You don't know what the integer is, but you know they belong to a 4-track parabola. So you plot them linearly in that integer, not quadratically. And then what you see is patterns jumping out. And what are these patterns? Well, this is the branch that you started with. And there are other branches that have a similar 4-track parabola, and so they will appear here. There is this white strip on either side of the line and that's because there can't be lines too close to the lines you are looking at because they have width, and so you generate this nice, and then there's a break in the pattern here. That's the band origin. And there are little things like this one. That's a perturbation. And there are a whole bunch of lines converging to a point. That's the band head. And there are often several branches that appear. And so this thing picks out, you start out with just a little bit, and it picks out the whole thing. And it captures the thing you most want, which is this. And from how many lines that are missing, it tells you what the omega of the lower state is, or the upper state, because you can't have a line, you can't have J smaller than the projection of J. And so there'll always be a certain number of points missing here. And so that's one of them. And I just think these are so wonderful. Here's another. I don't know which way. I guess that's up. And here you see, again, the band head is here. The origin is closer to the head, but it's much, the gap is much larger because the omegas are bigger. And there's a nice little perturbation here. And so this is useful because if you have a perturbation in the upper state, the same J upstairs is going to be perturbed. And here's the P branch, R branch, and here's the P branch. And so this provides absolute numbering. So you find the origin, you find from the width of this band origin region, the omegas, you get numbering from coincidences appearing in the red and blue regions of this plot. And so this is a no knowledge way of harvesting a huge amount of information. And it doesn't matter that you take a ridiculous number of differences because you don't do it. The computer does it. And then it plots it, and there's the intensity information is used. Okay, now, in the old days, we had very, very poor relative intensity information from a photographic plate. A lot of lines, but the intensities were only of qualitative significance. But we have chirp pulse methods where we get a big hunk of spectrum and the intensities are meaningful. So we harvest a huge amount of information, and if there is a pattern recognition scheme that would be applied to it, it would make use of the intensities. And this, yeah, well, it would make use of the intensities. And what would one do? Okay, now what else do I want to say about this? There are other kinds of pattern recognition. One of my former students, Matt Jacobson, developed what we call extended spectral cross-correlation. And the extended spectral cross-correlation is based on the expectation that there's going to be some pattern and some other pattern, that there'll be features in the spectrum that are repeated. So suppose we took two spectra and we changed the conditions for the two spectra. So suppose you have different isotopic species. And so one isotoper will give one spectrum. Another isotoper will give a different spectrum. Now, suppose we change the isotopic mixture and record the spectrum again. Then the complicated pattern associated with each isotoper will be exactly repeated. But the relative intensities of different patterns will change because we change the isotopic ratios. We don't even need to know how we change them. And so one can develop a pattern recognition scheme that says, okay, we have a certain number of exactly repeated patterns. Now, I thought I could do this without preparing. What do we plot? My goodness. I've cooked my goose. I'll have to come back to you on this, like a certain vice presidential candidate. But so what you end up is getting you have a scheme for picking out patterns without knowing what the pattern is or how many patterns there will be. And so this is amazing. As long as you have a complicated thing that is exactly repeated, and you can vary the conditions to cause the pattern to, the relative intensities of the patterns to change, you can pull out the individual patterns. And this is not limited to spectroscopy. It's, you know, you could, as long as you know that there should be patterns, you can use this in acoustics to learn about the shape of a room, or there's all sorts of ways in which you could use these cross-correlation ideas. There's another thing called, and I have to look up what the acronym means. It's cross-correlation ionization energy spectroscopy. Suppose you have a bunch of Rydberg series. So, so here is V equals 0 of the ion, and here is V plus equals 1 of the ion. So you have a Rydberg series converging to this, and another Rydberg series converging to that. So you have a complicated many-element pattern, which is described by the same equation, the Rydberg equation, R over n star squared. The the energy is given by, or the ionization energy. This is the Rydberg equation. So we will have several essentially identical Rydberg series converging to different levels. So you have this complicated thing, and you're looking at the spectrum, and it's a superposition of these converging patterns. And the resolution is poor, so you can't resolve all the features, but there are patches of each pattern that you can get. And so you move the patterns relative to each other, and you find the best overlap with the spectrum. And when you do that, you find you get information about the energy level structure of the ion. And this has been used to look at the benzene cation, where the rotational structure is very dense, and it works just beautifully. So there are all sorts of fantastic pattern recognition techniques that you can use. Do I have anything else? And now we're back to combination differences. Oh boy, how am I going to explain this? I don't think I can explain it. I don't think I want to explain it. When we do these sorts of tricks with classical spectroscopy, we get the whole spectrum all at once, and the information that enables us to assign it is concealed. And we have to dig it out. And it's not that hard to dig it out, but you need pattern recognition schemes that are not easily thrown off the track. The higher the resolution, the higher the precision, the more likely you will succeed. Suppose instead you have a laser, and you excite a transition with a laser, and you look at the fluorescence from that upper level. Well, when you do that, the spectrum consists of nothing but combination differences that are assigned, because they all come all of the transitions originate from a common upper level. The whole point of the pattern recognition is to find groupings of transitions that came from a common point. But if you tune your laser to a single upper level and look at the dispersed fluorescence, or you do a double resonance experiment, then you select a J, and you know what the upper level is, this level is, then everything is simple. And there isn't any real skill in assigning such a spectrum unless you're using this to go into an energy region which is so complicated that it's still hard. Even though you know the name of the level that you're going to, the good quantum numbers of the level you're going to, there's so many of them that you again are facing a difficult problem, which is now a physical rather than a pattern recognition problem, of saying, okay, I've simplified the spectrum, but I've still got so much stuff going on that I need a way of understanding what that means. And that requires having models, and the models are things that you conceive of yourself. I'm trying to go back to extended cross correlation and see if I can remember how this works. Yeah, I got it. You take this spectrum and you chop it up into resolution elements. And so you take, and you now have two realizations of the spectrum recorded under different conditions. And so you take a particular resolution element, and you ask, what's the intensity in spectrum number 1 of that resolution element? That's X. And the intensity in spectrum number 2 for that resolution element, that's Y. And so you plot a point on this intensity versus intensity plot. And then you go to another resolution element, and you plot a point. And sometimes sometimes you have zero intensity in one. Well, but if you have a pattern, what's going to happen is that the lines, they'll be emerging a ray on this cross correlation, which says all of the lines in this that contributed to this pattern. Remember, we had a spectrum where each spectrum had frequency information. We are not using the frequency information. We're comparing spectrum 1 to spectrum 2. And the frequency information is gone. It's intensity versus intensity. And so what will emerge if there's a pattern is a straight line with a slope which tells you the relative intensity of the pattern in the two different realizations of the spectrum. And so, and if there are several patterns, then you'll get several rays. And so, you know, this is a little bit counterintuitive because suppose you have only two spectrum. How do you get more than two patterns? Well, however many patterns there are, you don't, you know, the lines will have a, you know, all of the members of a pattern in the different realizations of the spectrum will have the same relative intensity. So you can have many. Now you could also have three spectra and do a higher dimensional cross correlation plot. Then you would have a ray in a higher dimensional space. And so once you see these rays, then you want to find the optimum value of that slope. And so you use a form of fitting, which is not least squares, but robust estimator. If there are features that are off the line, you don't want it to pull the line. You want to somehow get the information from the cluster of features that are near the line, and then you want to get the optimum slope. Once you have that, then you can go back to the original spectra and harvest the members of a pattern, because you know the ratio of intensities of the patterns in the different realizations of the spectra. And so first you find these correlation rays, and then you use the slope from them to separate the patterns. And it's really magical. And you know, people simply don't believe that this method could possibly work. But it works for isotopomers, as I described, but it also works for things we call polyads. And this is something that deals with polyatomic molecules, but it's really a beautiful thing. Suppose you have a group of levels that are anharmonically coupled. And so you have some kind of a matrix representation of this, and one member of this matrix, this group of levels, is bright, and so it couples, it lends its intensity to the other members of this group. And so if you can access a particular bright state from different upper levels, then it will pull out the same group of lines. And so it will actually, we use it to separate these anharmonically coupled groups of states. We'll come to that later. So there are many, many pattern recognition schemes. The old ones basically used frequency alone. With lasers and, with certain kinds of experiments, the intensities are very meaningful, and one can build pattern recognition schemes using the intensity as well as the frequency. And there are many people who will pay you a lot of money to find patterns in different kinds of data sets, even if the patterns don't exist, but you've got some very sensitive method that somehow multivariate, and you can say, yeah, you better put your money on that particular stock because I see this pattern.
Well, you know, it may not have been coincidental that Loomis was a stockbroker.
And Loomis was also instrumental in founding General Electric.
And also in radar during World War II.
Yep. So he was, he's a smart guy. But the actual realization of the Loomis-Wood plots, it's attributed to Loomis and Wood by Hertzberg, but it's a bunch of Swedes who had nothing to do with anything. They were old-fashioned spectroscopists who did. So I think I'm done, and I'm sorry that I froze up initially on the cross correlation, but if you have a complicated enough pattern, it just jumps out at you, and then you can use it to pull out replicas of it. And that's, I think, a really important thing.
I have one question.
Yes.
So having higher resolution improves the probability of getting correct.
Yes.
If you imagine slowly degrading the resolution and then seeing what's left as you start to degrade the resolution, do you start to lose, individual lines because you can't resolve, this combination of step? Or below a certain threshold of resolution, do you essentially lose everything? Either because everything important in a spectra is at the same resolution scale, or because in order to get anything, you have to use everything?
Well, your question is really a good question, as usual. But it uncovers, if you vary the resolution, if you degrade the resolution, it actually provides you with a way of disentangling dynamics. Because you know that if there is an off-diagonal matrix element between two states, two zero-order states, the eigenstates can never get closer together than twice the matrix element. So if you degrade the resolution, you will start lumping together features that are weakly dynamically coupled. And so it's a way of undoing the unimportant couplings and recovering the most important features. This is called Parsimonious Trees. It's a technique that was developed by Steve Coy, and it is a way of really understanding the dynamical mechanisms. What you look at is you have the original spectrum, and you degrade the resolution. And at some degradation of the resolution, some lines disappear. Those are called nodes.
Do you degrade the resolution numerically?
Numerically. You start with the highest resolution spectrum. You never degrade the resolution experimentally. So you have this thing, and you're degrading the resolution, and each time a line disappears, you plot a point, or you show that these lines are joining together. And from the distribution of nodes versus resolution, you get some kind of information about the distribution of coupling strengths. Now, I don't like this method at all. I think, you know, it would be wonderful if you have groups of things that originate from a common zero-order state that are not overlapping, but they do overlap. And so when you degrade your resolution, if there are features in the spectrum that start to get blended that have nothing in common, well, you have a crude statistical method that is being overloaded with spurious stuff. And I think that there are much better ways of learning about dynamical pathways and hierarchies of coupling than parsimonious trees. But it's a wonderful technique because you start with the spectrum and you just do something simple with it, and you plot the nodes versus resolution, and you see that there are sharp breaks in the number of nodes, but that will be corrupted by the different branches in the tree. You know, you look at a tree, if you could make the tree a two-dimensional tree, it would be great. But it's not, it's a three-dimensional tree. Okay, so you have any more questions like that one?
So let me just re-ask the second part of that same question, which is that obviously in a limited case with no resolution, you don't know anything. But is there a certain case for different kinds of spectra that if your resolution was below some certain threshold, you would basically not be able to assign any rotational lines? I mean, all right, obviously also maybe if your resolution was below some integral factor of b, that would also be bad, but.
Well, I don't have a good answer to that question. It's certainly true that if you're going to make assignments by logarithmic strip or combination differences, you need to have resolution that's better than 4b, because the combination differences change in steps of 4b. And so, and if you want to be reasonably free of false positives or whatever, it wants to be a lot better than 4b. So, and you can do you can make a statistical analysis of how many spurious combination differences will you have if your resolution, so the scale factor is 4b. And so if you have resolution of 1% of 4b, then you can probably guess that you're going to be wrong 1% of the time. That's probably not quite right, but it definitely gets better the higher the resolution. And but you know, if you have hydrogen as opposed to iodine, you know, the resolution needed for iodine is much better than for hydrogen. But for hydrogen, because the rotational constants are so big, you don't see many patterns. And so you know, you have a different kind of problem if the related things are very far apart versus when they're very close together. And so you always depend on redundancy, some kind of redundancy.
Okay. And then let me ask my final question. Today,
yes.
What is the limiting factor in doing resolution of rotational spectroscopy, or is there one? That is to say, are very heavy molecules, you know, difficult because, you know, you can't reach that resolution threshold of something like 4b, or is it the problem really just, you know, intensity assignment if you want that kind of resolution? Or
well, in a laser experiment, you're usually limited by the Doppler effect, unless you're using a clever trick to get rid of the Doppler effect, either by having a supersonic jet and looking perpendicular to the skim jet so there isn't any velocity in the direction that you're looking. But sometimes all of the all of the clever techniques for improving the resolution will never get you to high enough resolution unless you say, okay, I'm not going to do electronic spectroscopy anymore. I'm going to do microwave spectroscopy. I'm going to look at the level diagram in a different way. And basically, if you're careful, you do any kind of spectroscopy, you get, without a tremendous amount of effort, a part in a million frequency resolution. So a part in a million at 50,000 wave numbers is much poorer than a part in a million at 50 gigahertz. And so, but I mean, there are going to be fundamental limitations, like if you're not Doppler limited, you're going to be limited by the homogeneous line width. And the homogeneous line width has to do with how fast does the population decay or dephase. And one of the things that you're always up against if you have a sample of gas is the collision rate. And that produces phase-interrupting collisions, and it broadens the lines. And once you're up against that, you're finished. Unless you can, and you say, well, okay, I will go to lower pressure. But if I go to lower pressure, then there won't be any transitions. There won't be any intensity in the spectrum. So, yes, I think I answered your question. So we'll talk a little bit about laser techniques for assigning spectra next lecture, or something else that I decide I'm going to be interested in.